Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to use trig substitutions. Again, this is different from integration by parts, different from U substitution or the use of basic integration techniques. This is a brand new approach to tackle certain integrals. And we're going to make use of the Pythagorean identities like here. Okay, so we have three different kinds of that. And for each kind, in fact, there is one case. And this is like what I'm going to show you in a sec is applicable whenever you have the difference of squares or some of the squares popping in integrand. Let me just show you what they are quickly because I'm going to use them in the videos, and I'll explain them in the videos separately. But let me just quickly go over that. So here we go. I have integrals, let's say, involving the term radical a squared minus u squared. And when you see this type of expression in an integrand, what you're going to call is u equals a sine theta. Okay, this is a u substitution, but it's a trig substitution. And whenever you have a trig substitution, you should have a right triangle coming along with that, because here sine theta in the boxes you see is u over a, and I make up a right triangle right here. Okay, I place the theta right over there, so the opposite, which is this side here, divided by hypotenuse, is what's called sine theta. So that's u over a, okay? Because I started with u over a for sine theta in my substitution. And you find the other side by using the Pythagorean identity. So radical hypotenuse squared minus this side squared is, in fact, that side over there. Okay, so whenever you see this kind of expression, rely on to this. Let me just tell you one more. All right, I'll just show you one more, but there's in total there are three of them, and whenever it's applicable, I'm going to mention the corresponding version in the video. So if you have the terms involving like radical sum of the squares, where you have the number squared plus the variable squared, you have to rely on to a trig substitution, u equals a tan theta, and tan theta follows from that as u over a. So again, I'm making my triangle here, right triangle here. As you see, I place theta right over there, and tan theta by the substitution is u over a. Here we go, opposite divided by adjacent. That's how I place my a. Okay, so the hypotenuse is found by the Pythagorean identity. So that's radical sum of the squares of the sides. That's a squared plus u squared. Okay, there's one more for the trig substitution, u equals a secant theta, but I'm going to stop this video because it's already long, and whenever it's necessary, I'll bring up this slide, and first I'll explain on this slide before I solve the corresponding problem. All right, let's get started. All right, let's start with part A. We have 4 over x squared, radical 16 minus x squared. By the way, you can go ahead and check that the known techniques would not be able to apply here, like integration by parts or any kind of like u substitution other than a trig substitution. They won't work. So let's just look at what this kind of like trig substitution x equals 4 sine theta does. To understand that better, if you have an integral involving a number a squared minus a variable u squared, then u equals a sine theta is a very good substitution to work with, because a squared minus u squared in that regard is just a squared minus a squared sine squared theta. And we can make use of the Pythagorean theorem by first pulling out a squared and then replacing 1 minus sine squared theta by cosine squared theta. So in turn, the radical a squared minus u squared becomes the square root of a squared cosine squared theta, and that is a cosine theta. And that's exactly what we got here. So this way, as you see, that I can get rid of the square root of the difference of the squares completely, and I can rewrite that expression in terms of a trig function. In this case, it's a cosine theta. Okay, And whenever we have a trig substitution, that should come along with a right triangle. And I have this right triangle here. I placed theta here. Okay, this is my theta, so that I can read out some data here, because here sine theta coming out of this is u over a. Okay, so how you construct this right triangle is the following. So once you have sine theta equals u over a, then since I placed the theta here, so sine means opposite divided by hypotenuse. Here we go. This is my opposite. This is my hypotenuse. So I'm looking at the ratio u over a. Okay. By the Pythagorean theorem, this side is found by taking the square of the hypotenuse and subtracting u squared from that and taking the square root. Okay. So this side is like a squared minus u squared and square root. Okay. So this allows me to write maybe cosine theta out of this. As you see, cosine theta is adjacent divided by a, and that's exactly what I got here, because if you multiply both sides here by a, right? If you multiply both sides here by a cosine theta equals exactly what I got here, a squared minus u squared and square root. Okay, so we're going to sort of like try to utilize this concept here, but in the future you will see that whenever you have a trig substitution, a right triangle should come along with that. You can place theta here or theta here, it doesn't matter, as long as you just place the data correctly here, because then sine theta is going to be u over a, and u then must pop here, okay, because it's opposite divided by hypotenuse. It just doesn't matter where you place theta, that's what I'm trying to say. And I just placed my theta right here, and you can just go with that, or you may have your own right triangle aligned in a different way. Okay, let's go back to the example and keep working on this problem. So I have x equals 4 sine theta substitution provided in the statement of the problem. So I'm going to look at the differential here. So dx equals the derivative of 4 sine theta, which is 4 cosine theta d theta. So now, one by one, I'm going to replace all x-related terms in the integrand by theta-related terms, okay? But first of all, let me just write what this expression is out of this substitution. 16 minus 16 sine squared theta, and that is by the Pythagorean theorem. It's 16 cosine squared theta, okay? So now let's just go ahead and write down the theta formulation of this integral. So this is x squared, so 4 sine theta squared. I have 16 cosine squared theta in square root. And I have dx, which I have just found as 4 cosine theta d theta. Okay, let me just put a nice border here so that things are not going to be messy. Okay, all right. So let's see, let's try to simplify this. Okay, this is equal to 4 16 sine squared theta, and radical 16 cosine squared theta is just 4 cosine theta. Okay, 4 cosine theta, and then this is all multiplied by 4 cosine theta d theta. As you see that everything is written in terms of theta and there's no x anymore. Okay, let's observe cancellations here. So I have this 4 cosine theta canceling this 4 cosine theta in the bottom. Okay, and I have this 4 canceling maybe 16, and then you still have 4 in the bottom because 16 is 4 times 4. All right, I'm going to rewrite this integral in the simplified form. It's d theta over sine squared theta. But I know that 1 over sine theta is cosecant theta, so this is in fact cosecant squared theta d theta. So the good news is that this is a known integral, and you can go ahead and check the review of integration rules and look at number 15 here. All right, so cosecant squared u du is integrated as minus cotan u. All right, so that means I know this integral exactly. That is minus cotan u du. Okay, so let me just write that down here. So my u is theta. So essentially this is equal to minus cotan u plus c. Okay. So now in the next slide, you will see that I'm going to rewrite this cotan theta. I'm sorry, not u. Okay. Cotan theta plus c. I'm going to go back to the original variable. I have to go back to the original variable because there was no theta in the beginning of the problem, but I have this trig substitution, so we have to back substitute theta. All right, this is me writing the result in a cleaner way. So I have minus cotan theta. So to go back to the original variable, that's when we use the so you have to use the right triangle, and this is the time to use the right triangle. Let's go back to the right triangle here. Okay, I need cotan u. It is essentially I had the x equals. Let me just maybe rewrite the or redraw the triangle here. Okay, let's just do it together. Okay, so this way you can see actually how I do this. Okay, so I had equals x equals I had the substitution x equals 4 sine theta. So sine theta is x over 4. Okay, out of this. Well, sine is opposite divided by hypotenuse. So here we go, x and 4. So that means this should be 4 squared minus x squared, right? 4 squared minus x squared. In other words, it's 16 minus x squared. Okay. So to conclude here, that I need negative cotan theta, and cotan is adjacent divided by opposite. Okay. So minus adjacent 16 minus x squared divided by x, and I have the minus sign here, okay, and I need to put plus c here. So in the final shot, to back substitute theta, we have to have the triangle so that we can have the final shot, like final result in just one shot. All right, I'm going to finish this video here, and please watch the next video, which is going to be all about part B. Thanks for watching.